Here's just an outline for the topics I'll cover today. I'll start talking about high-performance computing and the path to exascale. Some of this will look familiar, as my predecessors have talked about already. Maybe I'll highlight a couple of different dimensions on that path. I'll talk about the next grand challenge for, I'll call it advanced computing. It's not just high performance, but I think there are challenges that will appear at all scales of computing. I'll talk about the Data Model Convergence Initiative. And here, this is where, Nicholas, when you first invited me to speak at your conference, this initiative was only 2 months old. It was at the very beginning of this initiative, and I'll spend a little bit of time talking about that. And then I want to close with some thoughts about continuum computing, which very much is related to some of the most recent talks that Ava gave, for example. Okay, so the path to exascale. We've had over 2 decades of massively parallel processing computers. We're now seeing the impacts of the limits of Moore's law, and we've been dealing with the end of Dennard scaling for probably close to 20 years now. Obviously, we all know that the #1 system on the top 500 list is Frontier. This graphic is an interesting one. It just plots and names the #1 machines on the top 500 list. And I want to dig into the milestone machines. And I guess this is, maybe it's an artifact of politics, but it turns out all the machines that crossed the milestone were actually DOE machines. The first one I was actually involved with is a teraflop machine, or ASCII Red, at Sandia National Labs. This was a system that used, I think, if I recall correctly, over 3,500 Pentium Pro processors, the desktop processors that Intel called COTS, commercial off-the-shelf processors. This system was interesting. It had a custom interconnection network called Cavallino, and it used a lightweight kernel operating system. But beyond that, it was very much the same kind of processor, same memory that you would have found on your desktop machine or server. This machine crossed the teraflop milestone in the summer of 1997, and it consumed 850 kilowatts. About 11 years later, as was mentioned earlier, the petaflop milestone was crossed by the Roadrunner system at Los Alamos. This system used AMD CPUs and IBM Cell gaming processors for their accelerator. It was integrated by IBM. I guess I should say, I didn't mention it, the ASCII Red machine, in addition to using Pentium Pro processors, was actually integrated by a division of Intel called the Scalable Systems Division. It was dissolved shortly after the delivery of ASCII Red, and I can talk, I'd be happy to talk to any of you about the history of that over a beer. But the Roadrunner machine was integrated by IBM at Los Alamos. It, in a very real sense, was the first hybrid accelerated system using AMD CPUs and again, those cell processor accelerators. So that was 11 years later, and it consumed 2.35 megawatts of power. And then by comparison, last summer, the Frontier machine at Oak Ridge was the artifact, as Doug mentioned, of many, many years of investment and effort. It crossed the exaflop milestone and consumes over 21 megawatts of power. So we think about this, right? From the teraflop to a petaflop, that's 1,000x improvement in performance and double precision floating point. The power requirement increased by about 3.7 times. And we moved from simple CPU compute nodes to hybrid compute nodes. In the move from petaflop to exaflop, it took 14 years, and the power requirement actually went up by a factor of 9. It's still a hybrid architecture, and if I think we were talking about this earlier. If you project to what a zettaflop machine might look like, considering it took 14 years to go from peta to exa, maybe we would see it by 2040 if we don't have any further significant investments, and it would probably require 10 times more power. So clearly, 200 megawatts is beyond the capabilities of any of our facilities, and we'd be subject to criticism over the carbon footprint of our supercomputers. So I think that's not very likely, and so there's really a grand challenge ahead of us. And I wanted to call your attention. Many of you may have seen this report and heard about within the U.S. the President's Council of Advisors on Science and Technology. Back in September of last year, they issued a report, and there certainly was a recommendation that I think was directed at the Department of Energy. It was a recommendation that the DOE take on the mantle and the challenge of reaching zettascale computing. And while that might be the right goal, I think we're going to have to think about how we achieve that goal. This report, this recommendation was part of a report looking at recommendations for the U.S. semiconductor ecosystem. So it's actually thinking much broader than just supercomputing. There's reference to NSTC, that's the National Semiconductor Technology Center. I'll explain a little more about that in a few slides. But I think the key point here is there's a grand challenge that has been, I guess, a marker put on the table that the nation should pursue a grand challenge to get to zettascale computing. Now, fortunately, this committee also made another recommendation that the Secretary of Commerce should establish this National Semiconductor Technology Center, and it should take on a range of different research topics, one of which I highlighted here, which is energy efficient computing and domain-specific accelerators. I think that's a key part of how we can address zettascale computing, and in fact, I'll say it again, computing at all scales for the future. Let's see, yeah. So let me move on. There's a similar report that's 2 years old now, issued by the Semiconductor Research Corporation. They issued a decadal plan in January of 2021 after 2 years of workshops. And one of the seismic shifts that they identified that's required is another grand challenge for advanced computing. And that was to get a million times improvement in energy efficient performance for computing. That's a driver for a lot of things. It's going to take more than a decade, but it's going to be a driver for quantum computing, analog computing, approximate computing, a lot of these non-traditional computing models. But nearer term, it's also a driver for maybe some other more conventional forms of computing that will involve extreme heterogeneity. The plot on the right-hand side here shows the gold bar at the top, which is the world's total energy production. I've seen some data that currently for 2020, the amount of energy that's consumed of the world's energy production that's consumed in data centers and supercomputers is between 1 and 2% of that total. But the projections are that by 2030, not doing anything, the energy consumption in data centers may climb to close to 20% of total energy production. To put that in context, yesterday, let's see, Jeffrey talked about the Haber-Bosch process, and we had some startling numbers for the amount of energy consumption for that production of ammonia. Fixing ammonia takes about, again, between 1% and 2% of the world's energy production every year. So that's where we are right now with data centers. It's about equal to the production of ammonia to fix nitrogen for fertilizers. But we've got a challenge ahead of us if we don't do anything. And this is why I think the SRC identified this as one of those seismic shifts that's required. So let me shift into the Department of Commerce. So the CHIPS Act that we refer to in the U.S. is a piece of legislation that was passed last summer. It actually established appropriations for the Department of Commerce at the, I think, $52 million level, or maybe $50 million level, and Department of Defense at the, I'm off on units, billion. Department of Commerce at the $50 billion level, and Department of Defense at $2 billion. So, yeah. But when we're talking, we were just talking earlier this morning about the investment that the DOE made in exascale, and whether it's $2 billion, $1.9 billion, or $4 billion, and then there are different ways of accounting for it. The CHIPS Act is a big deal within the United States. And think about it, it's more than just one agency within the US government. So the Department of Commerce is really taking the lead right now. Of their budget, about $39 billion is associated with manufacturing incentives. That's geared towards finding matching funding from state and regional governments and industry to put onshore and build fabs in the United States. And so we're seeing that already with announcements for fabs in Texas, Arizona, Ohio, Idaho, New York. So all of these are very significant investments in an onshore manufacturing capability for the U.S. I'll also stress that within the Department of Commerce and partnerships with Department of State, there's also a recognition that the supply chain is really a global activity, and so there's a lot of interest in bringing along allies for their roles in the supply chain. The Department of Commerce budget also includes $11 billion for R&D, and I'll describe shortly what the elements are of their investment. It also includes $2 billion with the Department of Defense for their microelectronics commons. And for the Department of Defense, they're very direct. They need that manufacturing capability to be onshore. Let's see. So there really are, as part of the CHIPS Act, there's an R&D vision that really covers technology leadership, which involves that R&D aspect for microelectronics. There's the ability to bring advanced ideas to the market. Really, what is characterized as bridging the valley of death from fundamental R&D to advanced products. And while the U.S. has always had leadership in fundamental R&D and microelectronics, the challenge has been how advanced technology concepts make the bridge from the laboratory R&D setting to advanced products. And so that's where some of the NIST and DoD investments are targeted. Talent refers to really workforce development, and that's not just researchers, but also the manufacturing workers, the technicians that staff the facilities for these production fab capabilities. So R&D elements, the main ones that I'll describe here are that NSTC, National Semiconductor Technology Center, and the vision for NSTC and its companion in the DoD Microelectronic Commons is to provide leading-edge hardware prototyping capabilities. Its goal then is to take R&D concepts from fundamental research and prove them with hardware prototypes. And then once you have hardware prototypes, you can sift out what works, what doesn't work, and then hopefully lower the technical risk for transitioning advanced concepts into products, or probably the next step is actually non-recurring engineering, advanced technology development, more sophisticated investments that are required to transition from an R&D setting into a real product. The structure behind NSTC is based on a public-private partnership. The vision is that you'd have some distributed technology hubs, some technology-centric hubs, and then some regional hubs in some kind of hub and spoke model. The actual structure is still to be determined. Elements that are in the NSTC include, again, prototyping of devices at the leading edge. And one of the key requirements for NSTC is actually to lower the barriers to entry, which means lowering costs, but also adopting approaches like open source technologies to make prototyping capabilities and testing capabilities accessible to a broader community. The next step in the NSTC process is for NIST to issue a white paper that'll be forthcoming in the next month or two. Another key element of the NIST R&D investment is the National Advanced Manufacturing Program. Jeff mentioned this in his talk as well. This really includes things like advanced packaging capabilities, plus the definition of standards. I think it was mentioned, Jeff mentioned UCIe, Universal Chiplet Interface Exchange or something like that, or Express. The Open Compute Project has something called the Open Domain Specific Architecture Standard. This is actually a good role for NIST to actually define the standards by which chiplets would be integrated and packaged on a silicon carrier to actually unlock an ecosystem and make capabilities more interoperable. And the vision would be something where you might have chiplets that are proprietary from one of the processor vendors developing CPU or GPU cores, and you'd have also the opportunity for customized accelerator designs that could be integrated with COTS processor cores. So some of the target areas really are, again, co-design, the leveraging the use of chiplets. I know the question was raised earlier, where have chiplets come from? They've been discussed for at least 5 years, maybe more. I'll agree with the comments that were made earlier. It's really driven by economics. But we see that chiplets can be the basis for driving an innovation ecosystem where, again, you don't have to reinvent and design everything as a monolithic processor. If what you need is memory interfaces, PCIe interfaces, you don't want to redesign CPU cores or GPU cores even, but you have to have an infrastructure, an ecosystem to integrate your technology advance into. And it's not just accelerators either. Your advance could be a memory interface, or it could be the interface to an advanced networking fabric. These are all technologies that could be implemented as chiplets and then integrated into a heterogeneous processor. I also wanted to mention the Industrial Advisory Committee. The Advisory Committee is making recommendations for the Department of Commerce on, on R&D gaps, on the governance model, how public-private partnerships might be structured, and on workforce development opportunities. And I'm honored to be one of the members of the Industrial Advisory Committee. I'm actually working in that subgroup, looking at R&D gaps and recommendations. One of the main things that we're doing is trying to identify where NIST should be making investments in their hardware prototyping and technology ecosystem and infrastructure, with the idea that many of the mission drivers, the challenge problems, will actually come from investments that still have to be made by other agencies. And so other agencies include the Department of Energy, NSF, NASA. DoD is already there to define mission drivers for their needs, but for the Complete CHIPS Act to be realized, appropriations are needed for these other agencies. And right now, that's probably a challenge for the US Congress. I will say, though, that the microelectronics technologies go also beyond computing, that it's new advances in processor concepts and designs, new technology advances in communications, in memory and storage, also in security and cybersecurity. These are all, I guess, recurring challenges that appear in many of the studies and documents that have been put forth as part of the US semiconductor strategy. So at this point, I'm going to shift gears and just mention the Data Model Convergence Initiative. This was, again, a project that was started back in 2019. It was funded by PNNL's internal laboratory-directed R&D program. And the idea was to define a co-design methodology and develop tools to support co-design. But our driver would be what we call converged physical and data science applications. So this is not convergence in the mathematical sense. This is integration of traditional physical science applications with data science applications. And as illustrated on the right-hand side, the idea would be that you'd have physical science simulations integrated with AI and machine learning methods, along with data analytics or graph analytics applications. These different types of kernels have different compute patterns, they have different data patterns, but the idea that you could have a heterogeneous computing architecture that could tackle these multiple modes of computing is one of the goals for the Data Model Convergence Initiative. To do this, we needed high-level synthesis tools that helped us develop concepts for reconfigurable heterogeneous architectures. And then we needed to support this with a software stack that supported the mapping of these converged applications to these heterogeneous computing architecture concepts. And what's shown at the bottom there is a link to the DOI for our leadership team's paper on this project. Expanding that pyramid on the lower right, what we end up developing are a series of open source software capabilities, open source tools. We have proxy applications that help define some of those different compute patterns. We have a series of system software capabilities, some of which I guess I'll outline in the next couple of slides. And then a set of hardware design tools. Again, all these have been open sourced. Links to those projects and their capabilities are in the URL shown below. So I wanted to highlight just a couple of capabilities out of DMC. The first is a compiler framework called Comet, and this was really to look at tools to develop domain-specific compilation that leveraged MLIR. And Andrew, I'm sorry I missed your talk. I had to get called away, but I'm going to hopefully catch up with the recording and review your slides. But I'm pretty sure what we've been working on aligns closely with your vision for how MLIR can support the mapping and optimization through compilation steps to different hardware targets. What might be our focus that it's a little different is that we've been looking at more than just a simple application. We've been looking at, again, these kind of converged applications. And I think that's a more natural fit then to mapping of different kernels, different compute and data use patterns to different accelerator types. But it's depicted on this graphic on the right-hand side. This compiler and DSL maps both dense and sparse tensor operations to a variety of different heterogeneous systems that have different targets for processor architectures. Let's see, I guess I'll move on. I also wanted to mention our work in some of our open source hardware design tools. And the SOTA synthesizer is a high-level synthesis tool. It's really intended to be something that will support hardware-software co-design. It's not going to compete with Synopsys or the commercial hardware design tools. It's meant to be lighter weight and simpler to help with design exploration of abstract machine models to develop architectural concepts and get them to the point where we can analyze them and develop implementations for emulation on FPGAs or CGA targets. We've been working on interfaces to, let's see, Andreas Olofsson's silicon compiler that was mentioned earlier, as well as the Open Road design capability from UC San Diego that was supported by DARPA. We can also interface to Open FPGA from Utah, and one of our other design tools called Open CGRA for coarse grain reconfigurable arrays. And again, it doesn't replace the commercial tools. It's not, but we wouldn't use this to design the, production grade hardware designs that you would want to have before you go to mass production. But we do think it will lower the barriers to entry for hardware software co-design. Along these lines, last summer we submitted to a NIST RFI submission with our colleagues from Sandia and Lawrence Berkeley, an RFI response to call for the development of an open hardware technology commons. We had a number of university collaborators, including Columbia, UCSD, Utah. Our industry collaborators included Andreas Olofsson's company, Zero ASIC. And this was proposed as an on-ramp to the NIST NSTC, again, with the idea of lowering barriers to entry and the ability to support producing test hardware at the leading edge. And then I just want to close with a couple of slides that really align more with some of the later talks in the workshop. Last year I supported a series of workshops on co-design of AI for Earth system predictability. And one of the use cases that came up was the idea of integrating the E3SM climate modeling code with the atmospheric radiation measurement user facility data. And this, again, is a use case that Ava described that really looks at how you might integrate very large-scale, high-performance computing simulation with measurement and observation data. It's actually a good motivation for continuum computing. I know I have colleagues back at my laboratory that are interested in digital twins for atmospheric modeling, and this might be an example of that type of a use case. So I'll close with just a couple of comments regarding continuum computing, and let's say some of the applications could be these distributed scientific discovery workflows. They could also be something like control of a complex distributed engineering system. At my laboratory, we also do a lot of work in the smart grid and power grid control and resilience. So that's one of the areas where, again, continuum computing can apply. And I already mentioned digital twins. So some questions or some, I guess, topics to raise. If we look to the future and computing performance then tracks application operations across this continuum, I'll just put on the table that this might be something to be thinking about when we look at how we get to zettascale computing, that the computing operations don't have to be just inside the machine room. They could be distributed across the cloud out to edge servers and edge devices. And then performance is measured by time to solution for these workflows. Another question would be, what's the energy efficiency? What's the energy consumed in completing one of those applications, one of those workflows? And then, so a question for discussion perhaps is, what's more important in continuum computing, time to solution or energy to solution? And then other questions that we might discuss. What's the programming model? And maybe some of Ava's concepts for Pegasus and Chameleon certainly apply here. Pete Beckman may have some thoughts on these topics as well. What are strategies for fault tolerance when you have a distributed computing and data ecosystem? And with that, I will happily take questions.